All right, next page. These are in essence these 8 rules or tests that we talked about when we're looking at determining if a series is convergent or divergent. Most of the power series and the Maclaurin tests and the Taylor series tests and stuff like that we're looking at, we use the ratio test a lot because it was one of those ones that allowed us to look at one direction. Like we knew that anything less than 1 was going to be convergent. So it was simple for us to be able to figure that piece out. What we're going to do tonight, we're in essence starting the review for the test. We're going to look at the convergence tonight. So we're going to look at problems and we're going to decide which test do we need to use to figure out if it's convergent or not. That's what we're going to focus on today. I should have the practice test done up tomorrow, so it'll be posted up on my website, and we'll go over the 10 questions that are on the test on Tuesday. The majority of the questions, like 7 out of the 10 of them, will be like what I'm doing today. It's just going to be, is it convergent or divergent? And which test did you use to show that? The other 3 questions will be probably 2 power series ones and maybe a Maclaurin series problem, but I haven't decided which one I'm going to do for that one yet. All right. How much longer do you guys need to write this stuff?
Didn't even start buying one slide.
Okay. I'll give you 5 more minutes. But you have a picture of it, so you can always finish writing it down afterwards.
That was not your question.
All right, 2 more minutes, and we'll start doing some problems. There you go. Take a picture.
comparison tests.
I just skip the middle ground.
The I wasn't entirely sure how to.
So the comparison tests are where we were taking, there was two different types. There was the direct comparison test, and then there was the limit comparison test, which we'll talk about. I'll go over those in a second too. But basically it was looking at a problem and is there something that I can compare it to that is similar to it? So we'll definitely going to do another one of those in a few minutes. So, all right. So the point of those steps there, now that you've gotten written down, I can go through them a little bit quicker. So like the test for divergence, remember that was the very first thing you should always try. You want to see if the sequence goes to 0. If it does not go to 0, it diverges. It's as simple as that. So check that first. P-series and geometric series, those are ones that you want to look at quickly and say, okay, are they represented as a P-series or a geometric series? If they are, let's use those things. Comparison tests goes back to the P-series and the geometric series. If it looks like one of those, but it's not exactly like one of those, can I compare it to one of those? Okay, that's what the comparison test is. Alternating series test, if it's got that -1 in there, that's alternating. That's when we want to look at the alternating series test. The ratio and root test are popular. They work really well unless they go to 1. If it equals 1, I got to use something else. The very last thing you want to try is the integral test, just because it's the most work out of all of them to be able to use. Okay, that's why it's the last one. So let's look at this problem. Does it converge or diverge?
Diverge.
Why?
The bottom goes quicker than the top. Just maybe not that quick, but eventually.
Well, if the bottom goes quicker than the top, wouldn't it go to 0?
Yeah,
So
so
then that,
that's sorry, that diverges, yeah, right?
no,
If it goes to 0, diverges or converge.
Well, if
we
it
don't
goes
know.
To 0, if it goes to a number, then that would be. But if it like goes off,
Correct.
that's diverge.
Yes. So, but yes. So if the sequence goes to, or the series goes to a specific number, it converges. That's by definition what it does. So what number does this one go to then? Or can we figure that out? Or which test did you use to say that it's convergent?
With the first test,
The test for divergence?
yeah, I think it goes to 0.
Then you don't know it converges. That only tells you if it diverges. Yes. Yeah. So the test for divergence does not tell us it converges. If it did, none of those other tests would exist. It would be as simple as use that test, we're done. Okay, it doesn't though. It does tell me if it diverges. So the test for divergence just looks at the actual sequence, not the sum. So, and we're looking at the limit as n goes to infinity of that one piece. So in this case, as we're going to infinity, if we divided everything by n, in essence, we get 1 minus 1 over n and 2 plus 1 over n, which goes to 1/2. So this diverges by, as I'm writing the E and the S at the same time, for divergence. As that does not equal 0. That's the test for divergence. So in this case, it doesn't go to 0. It goes to 1/2. And that would mean that it diverges.
So if we got 0, that's
We don't know. We'd have to try something else.
off have to do something else.
Correct. Exactly. That we have to try something else. So, but that's why I said you always want to try this first, because this will eliminate a lot of possibilities. And for most cases, it's pretty quick for you to determine that. So, all right. This is how I'd want to see it done on the test. I don't just want to see diverge. I want to see diverges and which test did you use. And I should see some work there showing me that test. If you just put diverges, I will mark it wrong. Yes.
What's the word I'm looking for? The method of dividing everything by n.
Yep.
That is something we use throughout all tests, right?
Yeah, you do that a lot. Anytime you're doing a limit, you use that. Actually, you use that back in calculus 1 too. When you did the original, when you were looking, before you even did derivatives, you did the limit definition of a derivative and you literally were dividing by n's to cancel stuff out. In essence, basically, the reason it works is because if whatever you do to the top, you do to the bottom, it doesn't change the problem. And dividing by n's gives you that 1 over something or 2 over n's, which goes to 0 when you take the limit of it. So it eliminates stuff. So yes, very nice little rule. All right, let's look at this one. Don't just guess, try. All right. Again, as I said, always try test for divergence first. Just try that one, get it out of the way. This one goes to 0. So that doesn't tell, if it goes to 0, that tells me absolutely nothing. Okay. It doesn't tell me it converges. It doesn't tell me that it does not diverge. It tells me nothing. So we have to try something else. If we're looking at this problem, what would you like to try?
Do you mind going over how we got from square root of to third plus 1 to?
So I divided them all by end of the third because that was the denominator one.
Yeah.
So this really is end of the third over end of the sixth. Because when you put end of the third inside of a square root, it was end of the sixth. Because the square root of end of the sixth is end of the third. Because it's the 2. Because I have to put it underneath the square root to be able to do the divisions.
When you apply it to dividing by to the third, and then which is the same as saying multiply by
1 over end of the third.
1 over end of the third.
Correct.
And if you want to bring it into the square root, you have to figure out what's the squared.
Yeah, basically, because it's, remember the square root means divide by 2 for the exponent, like 1/2 is the square root. Remember, like,
Yeah.
the square root of n is the same thing as saying n to the 1/2.
Yeah.
So what number would I have to put here to make it? I'd have to put a 6 to make it to be the 3.
So you can't do. So you can't just put n to the third divided by n to the third.
No. Because n to the third, because you didn't put n to the third under the, you have to put n to the 6th under the square root. Because it's this, in essence, it was this whole, this is what was there. It was n to the third plus 1 divided by n to the third, which I then need to go that, and that goes to that, which goes to that, the first one. So this one goes to 0. So test for divergence fails. So what do we want to try?
There's,
Okay, why?
because there's a lot of numbers on the bottom and they're all pluses. So if you take away them, numbers gonna get bigger and bigger. Divided.
Would it get bigger or would it get smaller? If I remove a positive, so,
It's on the bottom now,
right,
so it gets smaller. More pluses, the smaller it gets.
right, but if I'm removing the pluses, wouldn't it get,
Be more, be greater.
okay, so the bottom is getting, so the fraction, the whole fraction is getting
Yeah,
bigger.
yeah.
All right, so in essence, you want to take this problem and change the bottom to, you want to make it comparable to 3 n to the third. Okay, so if you did that, and the top doesn't change, because I haven't changed the top, this is going to be bigger than that, correct? Okay. All right. Is that bigger than that?
Yeah, actually, yeah, because under, yeah, he's right, it's under square root.
But isn't, right, so this is actually bigger than that, right? Okay, so here's the problem. This is why there's 2 different types of comparison tests. We have direct comparison, which we have to determine if it's bigger or smaller. And we have limit comparison, which we don't. Okay, so in this case, because I can't really find something that might, like, that's always going to be, that I can do that to, but it does kind of look like, it's all polynomials, so it kind of looks like that p-series thing. So we want something that it compares to, that we would know, does it converge or diverge, and then we can do the limit comparison test to it. So what you're doing here is fine. We don't know the direction it goes, so we're just saying it goes to this. We'll say it goes to that, goes to this. So this ends up being n to the 3/2 over 3 n to the third. Which would be 1 over 3 n to the 3/2, because 3 minus 3/2 is 3/2. Right? Does that converge or diverge?
Bigger than 1. So wait. Diverge?
Why? Which test did you use to show that?
Equivalent to like the p-series thing.
Okay, so the p-series, so p is, in this case, is equal to 3 over 2. So that's greater than 1. Is that a divergence or convergence? That's convergence.
Can we go over real quick the expression of the errors?
Sure. I'm literally just eliminating all the addition next to the things. Because that, if you think about it, as you get insanely large, those things don't matter as much as the first thing.
Right, initially you had.
I had greater than.
Greater than, less than,
Yes.
you had, what confused me was you had that second one,
Was less than.
less than. No, you had it greater than.
Right. Oh yeah, this one was greater. That's greater than that.
Yeah.
But yeah, but that's greater than that one. Because if the top's getting smaller,
Yeah.
Yeah.
Why would that, wouldn't that? How would? I don't see how the greater than, equal than, or greater than, less than, how that relates to the arrows.
it doesn't. So, okay. So we have the two comparison tests. The first one's direct. Okay. The direct comparison test.
Yeah.
So they're both under a comparison test. They weren't separated. The direct comparison test states if I know a function converges,
Yeah.
and it is always larger than the function I'm looking at, that function is going to converge as well. Okay? If I have a function that always diverges,
Yeah.
and it is always less than the function I'm looking at, I know my function diverges.
So for this function.
We can't tell which way it goes. That's the problem. I don't know if it's always bigger than or always less
Yeah,
than.
because for this one, we started out, okay, that first one is less than that
Right.
second one. All right, we have a direction we're moving. All right, the second one is greater than the third one.
Right.
That direction, it's not.
Right, but I don't know now, is that one going to be greater than that one, for example? That's the problem.
So that greater than, less than test is no bueno now.
Correct. We can't use that. However, we can do the limit comparison
Now we
test.
do the arrow test.
Right, now we can use the limit comparison test.
Okay.
That doesn't matter the direction. It just means that they're similar.
So that first test with the less than, greater than, what's the name of that?
Direct comparison. So the direct comparison test states if the function is always is convergent and it's always bigger than the function I'm looking at, then obviously the ones underneath it has to converge too, because it's going to converge and the other one has to as well. Hold on one second. If it is always less than the function I'm looking at and diverges, then my other function has to diverge because it's obviously going to be bigger than that other function. Yes.
So does the limit comparison test work because it's bigger and bigger numbers, the lower order terms just don't-
Basically, yes. That's literally how the limit comparison test works. So because I know, and we want to go to something that we know, and that's where we're looking at the P series is typically one we go to because we can easily tell that works. The other one that we can use is a geometric series sometimes because we know those work as well. We have a very specific thing that this goes to that. So if we can compare it to a geometric series or a P series, that's the ones we want to use. Because we can determine if the original problem converges or diverges. Yeah.
So the limit comparison test, you just want to be careful on higher order. That's about it.
Basically, yeah. If it's going to a P series, yeah, you're just looking at the highest ones. Because as you get to the bigger points, these don't really matter much in terms of the actual limit. Yes.
Go up to that zero part. So that's the test for divergence.
That's the test for divergence.
And it's zero, so it's
Nothing.
that it gives nothing.
Correct. Which is why I said that tells you nothing. It only tells you if it converges. I mean, if it diverges, that's all it tells you.
Do you mind the right screen?
Yeah.
The way that you got to from n to the 3 halves divided by n to the third
Mhm.
equals 1 to divide by n? Is that how you got there? Or you divide it by,
I subtracted the exponents because they were the same base. So 3 halves minus 3 is negative 3 halves. So it just goes down the bottom.
and then that's in the form that we like, that's in the p-series form, and then we just apply the p-series.
Now we're using the limit comparison test. Yes, that one, yes. So the P series, it says the P equals 3 halves, it's greater than 1, so therefore it's convergent.
Oh, that's not the p-series test?
Yeah, that's the P series test. Yes.
Call it the limit.
No,
comparison test.
this is the P series for that one. We need to use the limit comparison to determine if the original
Yeah,
function.
we use the limit comparison test to bring it into a form for the p-series test.
Yeah. But we're not done with this problem.
Why aren't we?
Because we've shown that,
It is. convergent.
we showed this series is convergent.
Oh,
We know that we have to figure out now, is this series convergent? That's the limit comparison test. So we have to do this series divided by that. So it is the square root of n to the third plus 1 over 3n to the third plus 4n squared plus 2 divided by 1 over 3n to the 3 halves.
a little wonky.
So keep change flip. All right. So let's simplify this down. Now I know why the book didn't do this problem out. I said, now I know why the actual book didn't do this problem out. All right, so we got to simplify this one down. So we can. That's still not going to work. That's still going to go to 0. Why?
Can you factor out the ends?
No. Hold on. What do you mean factor at the end?
Start pulling out of every single one. So at the bottom, it'd be like 3 squared, 4n. That type of thing, and pull out the ends, pull out the ends.
But you don't have an n in the 2.
Yeah. But
So we
that's
can't-
like back it up top.
how do you do?
I have no idea.
I was going to say, breaking it down the way you're doing is not going to help. right, hold on. I'm just working through a few different ways to actually try to simplify the problem down before I show it to you, because otherwise I don't want you having to sit there and do it a million times while I'm writing out on the screen. You're welcome.
This is the ratio. Oh no, this is the, what is this?
No, we're still going to do the limit comparison test.
Oh, these are all comparison tests.
Yeah. Oh, okay. All right. That way works. It's annoying, but it works. Okay. All right. So we've got this on the outside that we somehow have to deal with this part. So what we're going to do, and it's not intuitive, we're going to take out an end of the third.
Wait a minute.
What?
That's what I just said.
No, you were saying on the bottom.
I said we'd be at the top.
Okay. You were going to get that?
But then,
Like, you were going to get that?
then I asked you how, and you said, I don't know.
Like, you were not going to get that.
Looks like it.
All right. So we pulled that out. We also have the 3 end of the 3 halves. Actually, let me finish writing that. And the 3 end of the 3 halves here. All right. This right here becomes end of the 3 halves. 1 plus 1 over end of the third times 3 end of the 3 halves. Which now becomes 3 n to the third, 1 plus 1 over n to the third. And now I can divide the whole problem by end of the third. So 3 end of the third divided by end of the third is just 3. 1 plus 1 over end of the third. I divide the whole problem by end of the third. Yeah, because I literally did this to simplify because I didn't touch the bottom. I was just simplifying the top. Because it was the square root that was giving, like, it was the number with the square root out front. It was like, okay, how am I going to finagle this to get, like, and this is not an intuitive way to do it. So this is not the first thing I tried to do. The bottom becomes 3 plus 4 over n plus 2 over n to the third. And now if we do the limit of this goes to 3 over 3, which is 1.
So
Yes.
you're not gonna-
No. The ones on the test I actually will have already worked out, yes. No. This is what, so
Just throwing it out there.
the book has a bunch of examples for these. And no, the book literally states, just tell the rule to use it, to do them. It doesn't say to actually do it. So, because it was literally using you to test the test. It's which tests are you using? So I'm like, okay, no problem. I'll just use these examples. And when this, like, now I know why they didn't actually solve it out, because it's an annoying problem to solve out. So, well, it is solvable. It's just not easily solvable. Okay, so limit comparison test states what? Does anybody remember?
Yeah.
If the series A, if you do the limit of n going to infinity with series A divided by series B, and if you know that series B is convergent, and if that Actually, I thought I knew.
You're close. You're almost there. Everything you said is right so far. If the series goes to an actual number, if the limit goes to an actual number, they do the same thing. So in this case, since it goes to 1, they're both converging. They do the exact same thing. So
So
since
if we went to 0,
no, it has to be greater than 0.
so if it's any other number.
And number greater than 0. Yeah, that exists. So like it can't go to infinity. So since this is convergent, my original series is also convergent because the limit goes to 1.
So when you divide the square root of 1 plus 1 over n to the third divided by n to the third.
Yep.
You can convert the divided by n to the third by divided by square root of n to the sixth. Is that correct?
What? This piece, right? No. So I didn't even have to do the square root because I'm dividing the top. I already had an n to the third out front. Since it was multiplication, that dealt with the division piece. So I didn't have to divide the square root by anything anymore. So in the original part, when I did this up here, I had the square root. So I had to put the thing in dividing it by the square root. Since I had something in front of the square root, which is why I did that crazy little thing.
No, I treated that as 3n squared plus
Right.
3n cubed plus
Got
square root of
Yeah, it's multiplied.
Yeah.
That was
And that goes to 0. And square root of 1 is 1. 1 times 3 is 3.
yes.
That goes to 0. Goes to 0. 3 over 3, that's 1.
Mhm.
And that's conversion. And then that's conversion. That means A is conversion.
Mm-hmm.
And this is via the limit comparison test.
Mm-hmm.
Just look like one of those ones you want to use the limit on.
Well, when you get it's the comparison tests you want to look at, does it look like something else? And one of the things that you learned back in pre-calculus, and you did a little bit more even in Calc 1, is that when you have polynomials that go off to infinity, in essence, all the variables except for the first one doesn't really matter. So that's really what you look at, like, okay, that's kind of what I have here. Like, how can I use that to my advantage? And that's where the limit comparison test comes in. All right, this one.
I wonder what this one could be.
I wonder.
Look at me going.
Which is this one? Huh? Oh yeah, I'm sorry, I missed what you're saying. Yes.
I just heard you normally so it's wrong.
No, I literally didn't hear you. Yes, as soon as you see -1 to the n power, alternating series. Alternating series, we need to test two things. We need to show that b to the n plus 1 is less than b to the n, or equal to. And we need to show that the limit of b, or as n goes to infinity, of bn equals 0.
I have it's in the form of sum of -1 to the n minus 1 times b to the n,
Yes,
or sum of -1 to the n times b to the n.
yes. That's what that is. This,
I don't see any sum notation.
that's right there.
No, but what's 1 and 2?
Those are the two rules that we have to test.
The rules where it has to be in the form.
Right. That's the original problem. It is in that form. We've determined it's in that form. These are the two rules. One, in essence, as long as you have that -1 to the nth power there, it's alternating. You can do the alternating series test on it. So in this case, it's alternating. The red is my b to the n. or B sub n, now I can do I can show my two things.
I'm assuming it won't do that easy. We're probably gonna have to like
Honestly,
factor it out.
no. Honestly, the alternating series for most of them, if you see that -1 to the end, you know it's an alternating series. Do the alternating series test. It literally is that simple.
Yeah, we're gonna have to pull it out, but that's what I'm saying. Like that once in the next period, once in the
Not normally. Most times it's just going to be shown there.
Oh, so now we just have to figure out if the sum of b to the n converges.
Correct. Not the sum,
Sorry,
the limit.
why? I wrote down the sum.
Yeah.
Pretty sure that's what it said.
It doesn't. It didn't. I can't. Here. Hold on a second. This is the alternating series test. That's the alternating series test.
I
And
wrote it based off the thing.
if the series is in this format,
Yeah.
then the alternating series test is the obvious solution.
It says right there, if the sum of b to the n converges.
Yes, then the series is absolutely convergent.
I just said, and you said I was.
Okay.
The sum of b to the n. I said that.
Yes. The
So
problem.
now we need to figure out if the sum of b to
No.
the n converges.
Okay.
That's literally what it says. Note that if sum of b to the n converges. So now we have to figure out if sum of b to the n converges.
Okay.
I can read.
You can.
Okay.
Yes. There's two pieces to this.
Yeah.
Okay. If we know the sum of the b to the n converges,
Yeah.
the series is absolutely convergent, and we can state that.
Yes.
We do why it says note that if.
Yeah.
We don't have to necessarily do that part because that is a function of the alternating series test, not the alternating series test. Okay. Remember we did the whole concept of absolutely convergent. If we take the absolute value of something, if that series is convergent, then all possible options of that is convergent.
Yes.
Right. That is what that piece is saying. So we have two ways we can do this problem, if you would like. We could say, okay, eliminate this. Is this series convergent? N squared over n squared, n to the fourth plus 1. Is that convergent?
Yeah.
If that's convergent, you can prove that's convergent, you're good. It's absolutely convergent, so my original series is convergent. Which I'm telling you right now would actually take you more work because you're going to have to do comparison tests to show that. The question isn't asking, is this absolutely convergent? The question is asking, is this series convergent?
No.
So all we need to do is the alternating series test, which tells me to have to look at two things. Does the series decrease? Which is what that first thing says. So as n gets bigger, does the series decrease? And does the limit as n goes to infinity of the sequence go to 0? Okay. So that is the alternating series test. So in this case, if you look at this, actually, let me not write all this in red. N plus 1 squared over n to the plus 1 to the fourth plus 1. That's going to be less than n squared over n to the fourth plus 1. Okay. We know that's less than that. That totally makes sense. That's true. So that's true. 2. Does the limit as n goes to infinity of n squared over n to the fourth plus 1, what does that equal? If I do, actually, let me write that a little better down there. If I divide everything by n to the fourth, this goes to 0. So it is convergent by the alternating series test, and we're done.
That was quick.
Right.
We gotta make these things a little bit easier.
If you wanted to use the note, you'd have had to show that this series, which you could have done this by literally direct comparison. This would not have been that difficult to do. So direct comparison, you would have said 0 to infinity of n squared over n to the fourth plus 1. We want to show that that's convergent, which was the note. I could say that n squared over n to the fourth plus 1 is less than n squared over n to the fourth, which this equals 1 over n squared. That's a p series. So p equals 2, which is less or which is greater than 1. So it converges. Since that converges and it is greater than this, that converges. So because that converges, is absolutely convergent. Either one of those will work. The problem is that note, not every sequence or series is absolutely convergent. So you could do this and come up with divergent. That doesn't tell you your original series is divergent. We just know that the absolute value is divergent. You would then still have to go back and test your original series. And that the one perfect example of that is the harmonic series. 1 over n is divergent. So if this was n to the third over n to the fourth, it wouldn't be absolutely convergent. Because that would diverge. Because that was going to be the harmonic series.
So,
And then we would have to go back and try something else.
going for condition 1, condition 2, and
Will always work for an alternating series.
okay.
Okay. And if you look at this part right here, condition 2, that's the test for divergence. So if it doesn't equal 0, you know your series diverges because it failed the test for divergence. And if it equals 0 and it's an alternating series, it's convergent based on the alternating series test. The only time that it wouldn't is if this sequence increased. But if it increases, would the limit equal 0? No, the limit couldn't equal 0 if it was increasing. It'd be going up, right? So this basically confirms that. So typically when I do it, I will do 2 first, make sure it goes to 0, and then just show that as long as it equals 0, then I'll show that it actually is less than. Because if that doesn't go to 0, I'm done. I don't have to worry about it anymore.
And just to be clear, condition 1 and condition 2
Both have to be true.
satisfied
Yes,
for this test to give us a
Correct.
convergent.
correct. Yes.
If one of the tests isn't satisfied, then we need to try a different test.
No.
Oh.
Then it's divergent.
Oh.
Because it's going to fit. If it's going to fail something, it's going to fail number 2. Okay. I honestly don't think I've ever seen a question that has passed question 2 or passed condition 2 and it failed condition 1.
I guess condition, like you said, it's
Right.
not baked into.
Correct. So, and if it fails condition 2, I know it's divergent because of the test for divergence.
You want us to qualify whether it's absolutely convergent?
If I ask for, there will be a couple questions that ask, is it absolutely convergent? They all will not. So if it does not ask that, you do not need to qualify that. So like this question, I just asked if it was convergent or divergent. You did not have to qualify if it was absolutely or not.
I definitely have to brush up on absolute.
Absolute convergence is really only 2 cases. The only time you're really going to be looking for absolute convergence is if you're using the root test or the ratio test. That's when you're going to see the absolute convergence.
Out of curiosity, do you have like a little blurb similar to that for like all your goals, something like that? Collegiate finds or
What, like I just did for the alternating series test? Or what? For like,
well, like just what you said, like I don't know, like those.
Not that I've
ones,
written
the only
down.
Ones that you're really gonna care for.
Oh.
Convergent, like little like I don't know, I guess like a little tips and tricks for like each one, like.
Well, that's kind of what we're going through. It's like, I don't have them written down, unfortunately. I probably should at some point.
Maybe in your book.
I didn't write that section, actually. Somebody else write that section.
Is it gonna be, 10 questions?
Yeah.
Like last time?
My tests are always 10 questions.
I was gonna say, yeah, so there's probably plenty of time to run a pretty good amount of tests on a lot of
There's
people.
7 questions that are going to be like this, of which probably 2 will be absolute will ask for absolute convergence.
There's no such thing as absolutely divergent.
No.
Okay. Yeah, I'm just going through my notes and I realized.
All right, next one. We have what in it? Well, it could be NK, whatever. It doesn't matter what letter. The only letter you'll never see like this is X, because X kind of means something else in this stuff.
What you thought last time?
No.
Yeah, I was gonna say, I might be-
What's in this one problem that jumps out at you as something that's weird? Factorial. You see a fact? Here's one of your little tips of glory. Yes, if you see the exclamation point, it's ratio test.
Like 100%?
Can't write like paper flip note.
Yeah. All right, so we're going to do the ratio test. So this was the limit as n goes to infinity of an plus 1 over an. If it is less than 1, it's convert. Greater than 1 is diverge. Equals 1 is IDK.
Google had a lot of those, right?
You might have one.
Oh, so this test can tell you,
Absolute convergence.
I was gonna say,
It won't tell you that so there's no such thing as absolute divergence.
no. What I
Oh,
was
what?
gonna say, this test can tell you if it's divergent or if it's,
Correct.
yeah, it's not like you do one test and.
Right. This is, yeah, the ratio test and the root test are one of the few tests that will tell you if it converges or diverges. So, which is why we use the ratio test for almost every problem that we were doing at the power series, because it gives me that range, which allows me to solve it and find things out. So the other tests don't necessarily do that. All right, so let's look at it. So it's limit as n goes to infinity of the absolute value of 2k plus 1 over k plus 1 factorial. Okay, I'm gonna do the keep change flip all at one shot because I don't feel like writing this twice. So once you've got it in this format, put things that are like things together. So I have k factorial. The k plus 1 is k plus 1 times k factorial. I have 2k times 2 over 2k.
How'd you do that?
The opposite of the exponent rule. Typically, you add the exponents to put the bases together. I did the opposite. I split them apart. Because that's
You get the K plus 1 times the K factorial.
because K factorials is every term going all the way down. So if I had 5 factorial, that's 5 times 4 times 3 times 2 times 1, right? Or 5 times 4 factorial.
Fine.
That's all that is. If it was K plus 2, I'd pull out a K plus 1 and a K plus 2. Because I have to get down to the K, for example.
This becomes,
All right. So now we can cancel stuff out that's the same. So those can cancel out and those can cancel out. So I'm looking at the limit as n goes to infinity of 2 over K plus 1. Actually, it's technically K goes to infinity. I just totally realized that. Which this goes to 0. Based on the ratio test, what does this do?
wait a minute.
If it's less than 1, it converges. Greater than 1, it diverges. If it equals 1, I don't know. This is less than 1, so it's convergent by ratio test.
Take off work just to study. Like,
It happens.
If you were paying attention last class, this question should actually look familiar. Wasn't exactly written like this, but yes. Do you remember we did e to the negative x squared? And we said,
Special for me.
well, what we found out was you can't find the integral of it. It is impossible to find the integral of that. So we used a Taylor series, actually, that one, to find what the answer came out to be. However, when I did that problem, I said, if we had x e to the negative x squared, we could do the integral because we then have the u substitution on it. This one is one of those cases, we have the n in front. It doesn't look like any other series that we do, so we can't not necessarily do we cannot do comparison tests to it. Looking at the limit of that one, it's going to go to 0 because e to the negative or e to the n squared is going to be on the bottom, is going to go there a lot faster than n. So it's going to go to 0 if you do the limit of it, which also won't be easy to find. So this is one of those ones that if you go through all these little tests and stuff, always go through these little things. Like, none of these are going to be easy for me to do. The last option is the integral test. So this one, we're going to do the integral test. You want to leave the integral test till last. Yeah. You don't want, like, if you can get away with not doing an integral on these, don't do an integral. That's the integral test. The integral test, there's 3 things that has to be true for it to work. It has to be continuous, it has to be positive, and it has to be decreasing. Okay? Those are the 3 things that has to be true for the integral test to work. So if I look at x e to the negative x squared, is it continuous? Is there any value that's not going to work? If you want to look at it this way, it might help you a little bit. But is there any value that's not going to make this not work?
Your way the bottom would be 0.
Well, we're starting off at x equals 1.
Oh,
Because in essence, n equals 1. That's where we're starting. And it's always positive numbers going up from there. So there's no way for the bottom to be 0, right? So it's continuous. And that's actually a very important thing to look at. Okay? Because typically in a series like this, actually, first of all, it never actually goes, and it never ends up equaling 0. But if you had one that the bottom does end up equaling 0, but it isn't in what we're looking at for the series, you don't have to deal with that. So like if this was 1 over x, for example, 1 over x doesn't work at 0. But if we're starting off at 1, it doesn't matter. It's continuous. So this one's continuous. Is it positive? Can that ever be negative?
if we're starting at 1.
Correct.
it's positive.
It's always positive. So we never have to worry about the negative side. It's always positive in this situation. Is it decreasing? Yeah, this is one of those ones you could say the bottom's going to get bigger a lot faster than the top, so it's decreasing. There is certain situations where you're not going to be able to easily say that, so you would have to take the derivative of it and set it equal less than 0, so to show that it's always decreasing. If you can look at the problem like this and go, this is decreasing, I will accept that. So, all right. So it meets the criteria for the integral test. So let's find the integral. So we're looking at the integral of x e to the negative x squared. And we're going from 1 to infinity. Oh, sorry, dx. So how would I find the integral of this? Yes, I'm going to use u substitution. So u is negative x squared. So du is negative 2x dx. So negative 1/2 du is x dx. So I can pull out the negative 1/2. And I now have e to the u du, which ends up being just e to the u. From 1 to infinity. But I have to plug back in my negative x squared. So if I plug in infinity, what's this going to? What's e to the negative infinity? 0. Because that's in essence in the denominator, so it's 1 over e to infinity, which is 0. If I plug in 1, I get e to the negative 1, which is 1 over e. So this ends up going to 1 over 2e. Does that matter? No. All it matters is it went to a number. It converges. Since that converges, the original problem converges. So as long as the integral converges, the original series converges. If the integral diverges, the original series diverges. Okay? That's what the integral test tells me.
So it basically goes to 0 then No go, goes to a number, we're good.
No, it goes to zero. That's fine. That's a number. It wouldn't go to zero. I'll tell you that right now. Your integral should never go to zero.
So,
Because if your integral is going to zero, there is absolutely no area underneath that curve. Because the integral is telling you the area under the curve. So it shouldn't be zero. But if it does go to zero, technically it's still convergent. What
goes to infinity.
if it goes, yeah, if it's going to infinity, then that'd be divergent. Because even if it went to 1,000,000, it's still convergent because it goes to a number. Because what the integral test is showing you is that, remember, the integral is telling you the area under the curve. So if you're adding up a bunch of blocks under the curve, that's just the same as saying the area under the curve, except you're adding little extra pieces in there because it's rectangles and you're adding little triangle pieces when you do the integral. So technically the integral should be a little bigger than the actual sum is. But if the integral converges, then the sum has to converge because it's going to be underneath it. Yes.
Do you mind scrolling to
Yep.
one, right?
That's, there you go.
Real quick, how did we determine how did we plug in infinity?
I literally just plugged in infinity because remember it's going to be 1 over it's e to the negative x squared, so it's 1 over e to the x squared.
Oh, so it goes to
It's 1 over e to infinity, which is 0. Technically, you're supposed to do the limit as it's going to infinity and write all that stuff in. I don't, because it's not worth the time of writing it all in because you're doing the same thing by saying it. All right. This one. All right. What do we do first?
Do the root test.
No. What do you always do first? Test for divergence. Does this go to 0?
Yeah.
Yes. Okay. So we can't use the test for divergence. There's nothing really crazy in this problem that would force you to say, okay, I want to use the root test or the ratio test, things like that. There's no absolute value. There's no root n, things like that in there. So you're not going to jump directly to those. This doesn't look overly complicated, so we probably don't have to necessarily use the integral test. So the next couple of things we want to look at is it a p-series or a geometric series?
Technically, yes.
Technically what?
Be serious.
So p-series means it's something raised to a power, right?
Yeah.
So I have 3 to the n.
Yeah,
That's not
and no.
right, but that's not going to help me in the p-series. P-series says it's got to be 2 or 3 or 5. The n's got to be in the bottom. So n raised to the second power, that's a p-series. 3 raised to the nth power is a what? That's a geometric series. So this looks like a geometric series, except it's got that +2 in it. But I could say that that is going to be less than that. Correct? So this is the same thing as saying 1/3 to the nth power, right?
Oh. Oh wait, no, never mind.
Geometric.
same criteria for both.
For which one?
They both go to the n power. Like, why can't you apply the?
You can't. No. So you could apply the root test to this, the 1/3 n. You couldn't apply it to the 2 plus 3 to the n
Yeah,
because of the 2.
but
I don't need to at this point because that's a geometric series. I already know it.
oh, and you have an r.
Right. And R is what?
1/3 is less than 1.
And that's less than 1, which is the criteria for a geometric series. Technically, it's actually between -1 and 1. But-
Absolute value of r.
Yes. So that's less than 1. So that means it is convergent. This series is always bigger than my original series. So if this is convergent, this is convergent by direct comparison
Geometric series.
to 1/3.
So, it's not called the geometric series test.
Okay. This is the geometric series test. That wasn't the question I was asking.
Oh, because you're.
Correct.
Comparison.
Right. I use the geometric series test to prove the problem that I'm looking at to compare it to is convergent. And then I'm doing direct comparison to show that the original problem is convergent.
If we used. Do we have to say that we use? Because you're using two tests here.
Yes.
You have to say.
No.
which test.
If you put, just because I put that right there,
Yeah.
that tells me you do use the geometric series or geometric, geometric series.
I did have a question real quick. How did you figure out so quick that it does not go to 0?
No, I said it goes to 0
Oh, it goes to 0.
because it was 1 over something. If the top doesn't have an n in it or some kind of variable in it, I know the bottom is going to go to 0.
Oh, because the bottom's getting bigger.
The bottom's going to get infinitely large. The top's not changing. The only time that becomes more tricky is if there's something on the top and the bottom, then you have to figure things out.
I wrote down if limit of n going to infinity of a sub n is different from 0, then apply test for divergence.
Yes. If that didn't go to 0, if that right there
Yeah.
goes to anything other than 0, you want it. So the first thing you always want to test is that. If it goes to 0, I need to try something else. If it doesn't, test for divergence, I'm done.
So that is going to.
That's going to 0.
0.
So I can't use the test for divergence.
So why do I say then apply test for divergence?
I don't know. If it doesn't go to 0, you apply the test for divergence. So like, I think we did one of those, the very first one. I did.
Different from 0,
Not that one.
then apply.
Yeah,
test for
like this one right here.
Oh, I meant to write test.
Yeah, if it's different than 0. So if it doesn't equal 0,
Yeah.
you apply the test for divergence. This one, you wrote, read me how you wrote it.
I wrote it how it was up there. It
No, no.
says if limit of n approaching infinity of a sub n is different from 0,
Right,
then apply test for divergence.
correct. Which means not equal 0.
Okay, now that it doesn't equal 0, let's now apply the test for divergence.
Right.
Okay, so now we do the limit of n going to infinity of 1 over 2 plus 3 to
No,
the nth power. Because
this,
that's the test for divergence.
right.
All
But
right,
this,
now let's apply it, right?
okay, apply it. What does it get? What does it give
It
you?
gets me
0.
0.
Right,
So but it's not different.
right. So okay. What I said
Yeah.
is the test for divergence is the fastest thing to check. Okay. It's normally something you can just look at the problem and determine. Okay. In this one, I know it goes to 0. I didn't have to do any major calculations to show that it goes to 0. Because it goes to 0, I know the test for divergence fails. So I cannot apply that test. So I try something else.
Okay.
Okay. And then in this case, I noticed I had 3 to the end in the bottom. So I said, okay, that kind of looks like a geometric series. Let's try to compare it to geometric. All right, try this one.
Sorry, real quick.
Yeah.
Test for divergence is not finding.
Yes.
Cosine to 0.
All right, what do we want to try?
Question,
Sure.
is this convert?
Huh?
Is this converge?
That was my question to you.
On the -1 Trixie, and I was gonna say, let's do the alternate series.
Okay.
Right? And then we're looking at the rules, right?
Mhm.
The second one, it says, you take the limit of cosine of, and.
Actually, I think it's they use BN. Yep.
So cosine of 0 though is 4 over the square root of 2, right?
Huh?
Yeah, the finger trick. That's what I was using, right? So this side is sine, this side's cosine. 0.
Oh, okay. Square root of 4/2. Got it.
So it's converging.
Why?
Square root of 4 over 2 is 1.
Okay.
So it's not 0. So it converges.
We're not going to use Aiden math. Let's look at this.
That's not true.
You're going to see in a second. So BN is always the absolute value piece of it. So it's basically just eliminating the -1 because we know that this right here tells me to use alternating series test. So I'm just looking at the cosine of 1 over n squared. So this goes to cosine of 0, correct? Cosine of 0 equals 1, correct? Good.
All right, could you read it up to me? So if it goes to 0,
What's the test for divergence, Aiden?
if it goes to 0, it diverges. That's a limit.
What is the test for divergence say?
I don't know exactly what it says.
Oh, come on. Me and Eugene spent about 20 minutes talking about this one.
If it goes to zero, the test for divergence does not apply.
So then it converges, it goes to zero.
No,
No. The test for divergence,
No, it
it
just
doesn't,
doesn't diverge.
it doesn't give you a straight answer on convergence.
So I was basically right, just said the wrong word.
which made you wrong because there was only two options. So it's the bad thing about a 50-50 shot. Okay, so technically in this one, you didn't have to do the alternating series test. It fails the test for divergence because the limit goes to 1, not 0. However, it also fails the alternating series test, which because it fails the divergence test, it's test for divergence. Because the alternating series test says that has to go to 0. So, but there's no such thing as failing the alternating series test. You fail the test for divergence. So this one diverges. The other thing is, so one thing when I originally looked at this problem, is cosine always an alternating series? No.
Start from one or the
Right, because it starts at net positive 1 and it goes slowly to 0, and then it's from 0, then it's negative for a while, then it's positive. That, by definition, is not alternating. This one, however, is alternating because cosine is the only values that can be used for cosine is when cosine is between 1 or when the angle is between 1 and 0. Since the angle is always between 1 and 0, cosine is always positive in that situation because it'll always be in the first quadrant. Okay, so since cosine is always positive, this is an alternating series. If that n squared was on top, it would not have been an alternating series. So it also would have failed but it wouldn't have been an alternating series.
Because 1 is not 0, we know that it
Diverges, yes. Yes. This is why I think when I wrote, hold on, this one. Yeah. See how I wrote this one? 1/2 does not equal 0. Test for divergence. All right, let's do one more. Let's do that one. And a bunch of ones with trig functions. So let's do another trig function.
Are you dead?
Good, figure it out. What do we want to try?
I say it was a comparison test first. Get the negative cosine over the square root of n, right? Because the negative cosine is always between 1 and -1, like you were saying. And that's over n to the 1/2, and then it's decreases, and it turns out to be divergent. That last part might be wrong. Might be wrong. I just keep getting.
Okay.
Was that good?
For the most part. Till the end.
Yeah, the last part looked good.
All right. So we know that this, because cosine can never be bigger than 1, right? We know this is bigger than this. Which is 3 over n to the 1/2. Yes.
What do you want to, the, -1 from cosine, making it 5, that way it's definitely bigger. Maybe 5 over square root of n instead of 3 over square root of n.
I don't think it actually matters.
But
Because as this one gets smaller, so like if cosine is 0, 4 over the square root of n is going to be bigger than 3 over the square root of 0. Because the number on top is getting bigger. So that makes no difference, really.
But if he kind of make the,
I'm making sure that this is always smaller than that.
yeah, but the way to test for it is to figure out what the greatest value that cosine of n could be. And he's saying that to make it -1. So, is that what am I getting it right?
yeah, that way we have.
Yes. That way you can
always-
rule out all other values for n.
It's a beautiful day out.
Actually, it sucked for the majority of the day. It's freezing outside, but
Yeah.
it's finally the sun finally broke. Okay, in the end, in this problem, it makes 0 difference. Yeah, I get what you're saying. It doesn't actually make a difference in terms of the problem, though. This is a what? This is what?
Be serious.
He was right in that case.
Let's go.
All right, so it's 1/2, right? Which is
Less than
right, which means it.
diverge. Yes. I said diverge the first time.
I think you said converges.
Oh, I forgot what I said.
All right, so that diverges. This is always smaller than the original function, right? So the original function is always bigger than that. If this function diverges, then this one has to diverge as well by direct comparison. By direct comparison.
I just entirely misread my notes.
That's okay. As I say, in the grand scheme of this problem, it doesn't really matter.
That's the snakes.
Let's see. We've done how many problems today?
Probably about
Like
8, 9, maybe 10.
I think we did 8. So he was 1 out of 8. I wouldn't trust your instincts.
Yeah, I'll take one for you.
I wouldn't trust your instincts. All right. Your test will be posted tomorrow, probably tomorrow afternoon. I'm going to work on it tomorrow morning. Yeah, the review. We'll review it on Tuesday, and the test is on Thursday. What I will do on Tuesday is we're going to review the test backwards. We're going to do the stuff that I didn't cover today first. So
But what
Eight-
didn't we cover?
question 8, the power series stuff. The questions 8, 9, and 10, which is the power series, which I didn't cover. I'm going to do those 3 problems first.
We'll do the test backwards.
And then we will do questions 1 through 7 after that. Because if I don't get through them all, I literally just did that now. That's what I just did today. So if I don't get through all 7 of those questions, it's not the end of the world. But that's why I'm going to do it that way. Bye, guys.
Right.